meeting is now being recorded.
Hi, everybody. It's time to start. Good afternoon, ladies and gentlemen. Welcome to the Office of Information Management and Analysis Brown Bag series. This webinar will be strictly 30 minutes as usual. Just before we start the webinar, if people have some interesting topics for a webinar, please email us. Email me or Eric. You see our emails at the bottom of the announcement there. So today's presenter is Dr. Andrew Gray. He is an assistant professor at the University of California, Riverside. Andrew is Andrew is an assistant professor of Watershed Hydrology at the University of California, Riverside in the Department of Environmental Sciences. He completed his doctoral work in hydrologic sciences at the University of California, Davis, where he focused on fluvial sediment dynamics in small mountainous rivers. Dr. Gray is now building a research group to investigate the role of fluvial sediments in determining water quality and fluvial geomorphology, with particular interest in coastal environments and role of humans and climate in controlling sediment production, contamination, and transport dynamics. With this brief introduction, I will pass the phone to Andrew to start his presentation. So you can go ahead and start, Andrew.
Great. Well, thank you, David, for inviting me, and thank you all for joining. This is a little surreal. I've done some Skype presentations before, but never one where I can't actually see anybody or hear most of them. So that's something new, and hopefully it will be fun. So I guess I'll jump right into it. Today I'm going to talk about suspended sediment and sediment-associated contaminants, really with a focus on where I think the field is moving forward in terms of informing sediment management and water quality management. And so with that, there we go. With that, I'll jump right into talking about, just briefly introducing suspended sediment. So as most of you probably know, the suspended load in a fluvial flow or any flowing water are those particles that are retarded from their downward transport due to the turbulent fluctuations of the flow field itself, rather than direct interactions with the channel bed, which is bed load. The finest fraction of suspended load really displays almost no concentration gradient, with depth as well mixed, but as you get into coarser material in the suspended load, you start to get a concentration depth profile, and we'll kind of come back to that a little bit later. Fine suspended sediment is important for a number of reasons, including the fact that it really represents most of the surface area of solid material that's moving through fluvial systems. And that surface area has a number of implications, particularly when it's modified or augmented by the fact that a lot of that surface area is charged. And this leads to the fact that fine suspended sediments are really responsible for transporting a number of surface-associated contaminants and fluvial constituents through rivers and streams and to our coasts, including heavy metals, pesticides, herbicides, some nutrients, organic carbon, and much of the microbia as well. So, but a sort of essential tension lies in the fact that unlike certain human-produced contaminants that we're concerned with in terms of water quality, suspended sediments really found ubiquitously through all natural systems and plays important roles in the maintenance of aquatic ecosystems and landforms. With that said, humans have modified their environments extensively, and sediments overabundance and contamination has been found to really be one of the most prevalent impairments in water bodies around the U.S. and in California in particular. So the question that kind of comes out of this is, well, if we always have suspended sediment around, and when we're dealing with a really dynamic environment such as we have here in California with highly variable rainfall, high seasonality, high interannual to decadal variability, which drives high natural variability in suspended sediment abundance, the question then becomes, well, when is sediment really a problem? And if we're going to try to manage it in some sense, then we need to know more about where it's coming from, what's driving its abundance and its dynamics, and potentially contamination, in order to inform us how we can manage it. And some of this really gets back to also understanding the temporal and spatial scales of sediment transport through these environments, which is often overlooked, and I'll touch on that briefly today. So if we, say, zoom into the organizational scale of a watershed, and in this case, as an example, I'll pull up the Sacramento-San Joaquin watershed. This highlights one of the issues that it really is a result of having suspended sediment play potentially important roles, but also act as a contaminant. And oftentimes that takes place these days at different parts of the same watershed in the same system, or also you can have competing sort of roles of suspended sediment within the same reach of a given system. So here, say, in the Sacramento-San Joaquin watershed, if you get down into the Sacramento-San Joaquin Delta and the Bay, where you're experiencing regional sea level rise, really mineral sediment, suspended sediments required for wetland accretion in most of these kinds of systems. There's also a long issue of legacy sediments that have been contaminated with fairly recalcitrant sediment-associated contaminants such as PCBs, et cetera, that are already present in the base system and are prone to being resuspended and essentially reintroduced to the aquatic ecosystem if they're not covered by clean sediments. So this is really a situation where, in part, at times, for some of these demands, clean suspended sediment coming in can actually be thought of as a resource. Whereas as you go upstream into the interior lowlands and the uplands, well, we have clean upland sources, quote unquote, coming out of primarily the Sierra Nevada. Much of those have been disconnected through damming. There's, of course, well-known implications of that from a core sediment dynamic perspective, where we're sort of blocking off a lot of salmonid habitat from potential riffles and gravel-bedded reaches, and also shutting off the gravel conveyor belt to replenish the remnant habitat that's left. But also, it's resulted in a shift in sediment sources from these upland steep headwater catchments to agricultural lowlands that previously weren't such a large part of the sediment supply story, as well as some of these coast ranges, urbanized catchments that are directly on the bay, if you're considering that as your area of interest. And so there's this real shift from of sediment sources that really now concentrate on areas that have been highly modified by humans, both through urbanization and agriculture, with concomitant sediment-associated contamination effects. And so this is just sort of a illustration of how, if we're going to think about suspended sediment in aquatic systems, we really do need to take a watershed-based perspective, because we need to think about the demands for the reach or subbasin of interest for any particular study, or maybe there's some chronic condition that raises that up to interest. But we really need to think about water body services, both in that reach and also downstream, really from more of a holistic perspective. And of course, this needs to begin with human beneficial uses, aquatic ecosystem health considerations, and some of the stuff that spools out of that are perhaps ambient targets, which is what I think a lot of the field of water quality tends to focus on, are targeted conditions that we would like to achieve as they relate to the requirements of the aquatic ecosystem and the human beneficial uses of that system. And so the question then becomes, how can we inform management through investigations into sediment dynamics of these systems? And one way, of course, through monitoring, we can take snapshots or characterize the conditions within the streams. But I think more importantly, we can also get at causality and start to approach understanding the processes that are contributing sediment to these channels, controlling their composition, which ultimately gets at looking at provenance as well. And those are the sorts of things that can be really powerful in terms of informing management. So if we think about how fluvial suspended sediment, so river sediment in suspension, has been monitored over the years. There's two main approaches, ambient characterization and what I would call a flux-based approach or a watershed-based approach if that's applied in a distributed fashion. So the ambient characterization approach is really it's a dipstick where you're taking a snapshot of the abundance at a given time, whereas a flux-based approach incorporates the fact that you're dealing with a dynamic condition that's closely related to the flow of water through the stream. So you actually have to consider discharge as well. And so with ambient characterization, you can go in and measure a condition, whether it's suspended sediment concentration or more likely turbidity these days, bed texture or some other things as well. The issue is, when we actually look at contaminants that are associated with sediment, it's almost never characterized directly from this flux of material through the system in suspension, but rather by sampling channel banks or channel beds. Mostly, I think, because it's much easier to deal with the amounts of sediment that are required for those kinds of analyses. If you're collecting something directly from the bed of a river, you have mostly sediment with some water mixed in. If you're collecting it in suspension, you have to refine it to pull that sediment out, and that can require liters, hundreds of liters, or even thousands of liters for centrifugal refinement. And so with ambient characterization, it's usually a snapshot. There's no discharge information collected. And for that reason, we can't really get at flux, and it strongly or greatly limits the kind of process-based insights that we might derive from collecting those information. So if we're going to think about process, we, of course, again, have to remember that the delivery of sediment is highly connected to, and usually as a first order described through dependency on the delivery of water to the channel. And so if we're going to take a flux or watershed-based approach, we have to keep in mind, of course, that in dealing with watershed hydrology, we really have a convolution of internal and external factors that are conspiring to produce the expression that we're interested in, whether it's discharge or the materials that are being carried along by that water discharge. And by internal factors, I mean the actual topography, geology, vegetation, land use of the basin, and external factors are namely climate and other perturbations. So if we're going to go through the process of thinking about suspended sediment dynamics of a system, then we start really by thinking about these internal and external factors that are conspiring to produce discharge, so to really deliver water to the channelized system, and then it gets routed through the system largely on the basis of internal characteristics of the system itself. But those same internal and external factors are also interacting to introduce sediment to the channel. And much of it, of course, in most systems is actually being delivered along with a lot of the, at least, surface runoff to the channelized system. And for that reason, we generally find in many systems that discharge, and here on the bottom of this graph you see log discharge, and on the y-axis you see log concentration. Discharge is generally used as that first-order approach to explain the variations in concentration of suspended sediment. But really what we're doing is using discharge as a proxy for those same internal and external factors that interact to produce that sediment supply to the channel. And as you can see, as we get into these small watersheds, and this suspended sediment concentration discharge relationship is actually from the Salinas River down in the Central Coast. You can have a couple of orders of magnitude variation around that relationship, and that has to do with the divergence between these the supply and transport of sediment to and through the channel, and how that differs from water discharge. And then, of course, we can convolute all this to get at flux. But it's through, and so this approach in and of itself of just kind of looking at the dynamical change of the relationship between suspended sediment concentration and discharge, we can climb up into that and try to work our way back towards changes in internal and external factors that are driving changes in sediment supply and sediment character if we actually go after characterizing that as well. But we can only go so far with those sort of stochastic techniques. And really, if we want to refine our approaches to understanding really where sediment's coming from, it's greatly aided if we can actually go in and try to get after the sediment sources themselves, so erosion monitoring. There have been major advances in some of the techniques that are available for repeat surveys to actually look at erosion development over time, including terrestrial laser scanning, structure for motion, primarily off of drone platforms, LiDAR, airborne laser scanning, and aerial photographs. And, of course, as I mentioned, you could go through and then distribute that suspended sediment discharge monitoring throughout the watershed to get more of a watershed-based approach to look at sources and sinks by moving, monitoring below and above certain land use activities, et cetera. And there are also sediment fingerprinting techniques. But I should mention that all of these, of course, you're limited in some cases by the timescale of monitoring, well, pretty much in every case by the timescale of monitoring versus the timescale of the process. You can get around that to some extent if you're actually exploiting sedimentology. And in general, it's a high cost in terms of effort and the amount of money that has to be invested. And of course, it's the latter, the high cost of this situation that what really drives the fact that most suspended sediment monitoring is done in an ambient fashion. So if we're going to actually go out and do a flux-based approach, one of the sort of the minimum way to go after that is, you absolutely need to have discharge monitoring, and it's pretty easy to get continuous discharge data, particularly at those stations that are maintained by DWR or USGS or others. But then you also have to monitor suspended sediment concentration. And to do that in a really rigorous way, if you're interested in all of the sediment that's moving through in suspension, you actually have to take into account that concentration depth profile for coarser sediment. And it's pretty difficult. You can't really do this in a continuous fashion for the most part. But if we keep in mind that, if one of our major interests really is fine sediment and fine sediment-associated contaminants, then we can sort of skip around the issue of the concentration depth profile and get towards more automated methods where we're assuming or we can reasonably convince ourselves that the fine sediment is well distributed throughout the fluid depth profile. In this case, we can set up automated sampling stations. So here we have an ISCO automated sampler that's hooked up to an area velocity flow meter and also been a Campbell data logger set up with a turbidity meter and pressure transducer. And this way, we can develop turbidity, suspended sediment concentration rating relationships, and get at more of a continuous monitoring of suspended sediment dynamics. And also, by collecting samples, perhaps characterize those and get at the dynamics of the contaminant load as well. Now, the sediment-associated contaminants, they're pretty difficult to go after. As I mentioned before, very, very few studies have ever been conducted where the suspended load is actually being characterized for its contaminant load or for its composition. Because really, you need to have the suspended sediment dynamics analysis going on as well, and you're adding on this contaminant analysis that can require the acquisition of pretty massive samples, particularly if you're dealing with a system that has a fairly low suspended sediment concentration. And that high-volume processing requires large centrifuges or even more specialized continuous flow centrifuges. And the USGS is one of the only players out there who's done a fair bit of this work, along with a couple of other academics. And they've published some really nice guidelines on this just recently, back in last year. So as a result, we know very little about the transport dynamics of sediment-associated contaminants. And of course, these contaminants also are experiencing reactive transport and exchange with reservoirs of sediment in the channel and adjacent to the channel on their way through the system. And so I think, as I would argue throughout this talk, it would behoove us to try to make these investments, particularly in cases where we really do need to know more about how the contaminants of interest are moving through the system. Another powerful technique for thinking about where the sediment's actually coming from in the system, whether you're interested in the bulk suspended sediment load or also in the contaminants that are transporting with it. It's basically an approach where you characterize the source. So you have to go through and actually, in a distributed fashion throughout your watershed of interest, sample different reservoirs of sediment, analyze them for whatever constituents are of interest, whether it's trace elements, if you're trying to go after substrate differences that may be present throughout the basin, contaminants, and that may be bridged over by actually just knowing something or knowing more about the broadcast of those contaminants throughout your area, whether it's agricultural use, et cetera. Or another technique which involves employing fallout radionuclides that are basically coming mostly in association with sediment in the air and washed out, wrung out through rainfall events, interacting and being deposited on the surface of the earth and then being redistributed through erosion and sediment transport. So all of these approaches can be then, apply to a mixing model if you collect your integrated suspended sediment samples, which will then allow you to figure some things out about where your sediments are coming from if you have enough difference in the composition of your source sediments. And so these are some of the techniques that my laboratory is also starting to employ. So in my opinion, the future of sediment management could be greatly aided by some of these techniques. Obviously, I'm preaching to the choir when it comes to watershed-based plans because that's really a shift in aquatic management that's happened over the past decades. But it really begs the integration of sediment monitoring with aquatic and human requirements. And in recognition of the fact that we really do need this kind of more watershed-based, process-based monitoring if we want to figure out where the sediment's coming from, how it's being transported through the system, and then use that to actually inform us as to how we can reasonably approach sediment management. And if sediment-associated contaminants are really of interest, we need these sorts of approaches and also explicit acknowledgement of that what we're dealing, the fact that we're dealing with suspended sediment rather than just sediment that's sitting static in a channel or adjacent to a channel. And there are a lot of emergent technologies that I think are going to come into play that already are and should play a larger role over the coming years, including some of these remote sensing techniques, high-resolution surveys, and sediment fingerprinting. And I should also mention that a big issue that I kind of mentioned at the beginning of this talk, and I haven't gone into in great detail here, is the fact that sediment that's moving through these systems, even the finest phase of sediment, has a characteristic transport length and a characteristic transport time after it leaves the hill slope and enters the channelized system. And oftentimes that is entirely ignored when it comes to managing sediment and the kinds of sediment management recommendations that end up coming down the line often don't consider the time lag between management implementation and what you'll actually see downstream in terms of changes in sediment dynamics and abundance and character. So that's also something we can go after using some of these fallout radionuclide techniques in terms of and also sampling of channel beds, channel banks, and other transient stores such as floodplains. And so just to put that in perspective, there are over 150 303D listed water bodies in California that have been listed for sediment impairment. Of those, around 50 have TMDLs at this point. And of those 50, almost all of them have their TMDL attached to ambient targets. And very, very few are informed by flux-based monitoring or ongoing flux-based work. And in my opinion, I think that's a direction that we should move to more so in the future if possible. And so with that, I'd like to thank you all for your attention. And here's my contact information if you'd like to follow up. And I'd welcome any questions.
Okay, thank you. People are free now to ask. Did you unmute them?
All guests have been unmuted.
Yeah. Everybody is unmuted on the phone. You can ask.
We have to?
Yes, yeah.
Well, thank you very much for your presentation. Do you know about how much it costs to install the automated sample loggers?
Yeah, I can talk about the cost a bit. So, now if I click back up to that it goes sampler. Just the use scope part where you're collecting water samples and measuring discharge, that's probably about $7,000, $7,000 or $8,000.
And these are for ambient or for the flux?
So if you were going after continuous discharge monitoring using one of these area velocity flow meters, that area velocity flow meter is probably about $3,500, and this goes about $3,500 or so. And then some other odds and ends, yeah, that might drive you to around $8,000. Or, these area velocity flow meters are fairly limited. So you could also just have a pressure transfer and go in and if you're in a concrete channel like this, potentially use empirical approaches to back discharge from tape, or you can come in periodically, measure discharge and develop a stage rating relationship.
Thank you.
Sure. And another fairly cheap approach would be to take like a Campbell data logger or some data log hooked up to a turbidity or pressure transducer, and then just periodic sampling for sediment concentration and actual discharge, and then developing both of those relationships. And that would probably cost you, more on the order of $2,000 or $3,000.
Do you know offhand which of the TMDLs are using the Flux model?
So let's see. I know that out in the Imperial area, so like in the Colorado River regional board area, I know that some of those agricultural drainages were studied in a flux-based perspective, and I know that their targets are flux-based. That's one of the ones that I can't call off the top of my head. And if you wanted to follow up with me with an email, I can send you questions or some of those stuff you'd like.
Any more questions for him? Okay, thank you, Antu, and thank you all participants for participating.